Okay, so 11.34, what is the largest area? And today we are going to be using algebra, or in other words, we're going to be doing math, as I like to call it. We're just going to do some math, and we're going to find a maximum, which could also be, so we could find a maximum, or we could also find a minimum, depending upon the shape of our data. Maximum or minimum area. And so in this activity, you're going to connect and apply a lot of the knowledge of what you learned throughout the course to solve a fairly challenging problem. So our task today is to show four representations: a graph, table, equation, and situation. So the graph, the table, an equation, and then we got a situation of the problem. And we're going to create a poster looking thing that includes a drawing of the pen with the largest possible area. Largest possible area. We're going to state what the dimensions are, its height and its width. So we need to state the dimensions and use multiple representations to justify the conclusion that this is the largest area. So we're going to have to be able to prove this. You can't just sit and say, yeah, I got the answer. You actually got to prove it. And so multiple representations: graph, table, equation, situation. So we got to have a graph, a table, and an equation. Those are our three that we'll be using to justify the actual largest area. So our situation is this. Lucy wants to be a farmer like her dad. Her father says he will give her some cows to raise if she can build a good pen. And so a pen, that's just an enclosure. An enclosure where you keep the cows, just like this picture. And she's going to build it along a wall. And it's going to be a wall that rectangular shaped pen. This one only needs three sides because one side's the wall. So we know we got three sides against the family's barn as shown. And her dad is giving her, Lucy saves money and buys 30 meters of fencing material. So we have 30 meters of fencing. So that's all we've got. So the length of this fence, if we go around, can only be 30 meters. So we're held to that. So we got a little fact here from our problem that we have 30 meters of fence. And we're going to build a fence that has three sides. So we have 30 meters of fence, we have three sides, and we want to get the max area. So that those cows have the most area to move around in. So the max area to keep some cows in. Hopefully she's not going to have too many cows. So really, how long should each side of the fence be to give the cows as much roaming area as possible? And then how can we prove it? So that's what we want to get to with these two parts here. How long should each side be? So we have as much roaming area as possible. And then how can we prove it? Or convince her. So we have to be convincing. Not just, hey, I think it's this. It will be, no, it is this. And that's the difference. So since we talked about having to make a table, remember we only have 30 feet of fencing to use. And then we're also going to be graphing that information. So for our table, we're going to start out, we're going to try some different size pens to see which ones appear to give the largest area. Remember, we only have 30 feet of fencing. That's it. So we're going to make an XY table of that, and we'll be walking through that. And then we're going to calculate the area and try it, and then calculate the area for each pen that we try. and enter that data into the table. So the key is we just got to figure out, first of all, what is the pattern. So if we can find a pattern for the shape, it makes it a little easier. And that brings up, we're going to be looking for a relationship in the sides. And that will hopefully, the relationship of the sides will hopefully give us our pattern so we can then get all of them in there, as many as possible. And then we're going to graph it. So we're going to graph the data that we made, and we're going to be careful about how we scale the axes so that all possible pens fit on the graph. I included a massive graph, so we're going to make it close, but we're also going to venture into Desmos later. We're also going to use Desmos for this once we get our equation and compare the two. So where is x as small as it can be? Is there a point on the graph where x is almost as big as it can possibly be? So these two things right here are going to come into play. If we're missing pens like this, we're going to have to fill in all the gaps. Should x-intercepts be included? And what are the x-intercepts? Well, we know that x-intercepts are zeros. That's when y equals 0. And so, and should they be included in the graph, we're going to figure out whether they should be or not. So here's the thing. X is going to be the length of the side, the length of the sides of the pen that are attached to the barn. So if we have our barn here, just an idea, if we have the barn that's here, this is our barn, then the x values are going to be these two sides. This is an x, and then this is also an x. And then this side here is going to be whatever it's going to be. So this side is just whatever it is. This is what's left of the fence. So that's our whole fence part right there. And then the area is going to be our y value. So the area is going to be y. So if we were to take x length, or the height, whatever it is, one dimension, and we know that since we know that the area, and it looks like it's a rectangle, area of a rectangle is length times width. And the width is going to be what's left over. And by left over, I just mean it's not attached to the barn. So we're going to end up with something that looks like, it appears to be that it would be this times this value here. So the area of our rectangle is going to be the length, which is our x value, times whatever the width is. Take this out, and we'll just call that width. So this is our width. So if we build the pen up, we're going to have 1x here, which means this side has to be the same because it is a rectangle. So we have length times width. And if you look at it, we're going to figure out what that is. And so that's just how we get our area. So really what determines the width is going to be our x value. And apparently we have two of them. That's for dealing with the length of it. So we got an x, it goes wide, and then an x. All right. And then we're going to take that information, we're going to make a table from this, and then we're going to graph our table, and we're going to answer some of these questions. And look at it. And the first answer we can actually get at is this one here. should the x-intercepts be included in the graph? So if you look at this, if this is our x and this is 0, we have no pen. So we can't really include those. So the answer to this question is no, because our length per se would then equal 0, and you can't have a 0 area, which would mean then the area of the rectangle would equal 0, and we can't have that. We do not want an area of 0. So we've already taken care of that part, and we'll show you what I mean, or what it means, right here. So here's our barn, and apparently it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. It's 30 long. So if we have 0 and 0, that's 30. That's the maximum length of our fencing material, is 30. So there's 30 and there's 0. So if we stretch our fence all the way out along the wall, we don't have a fence area. We don't have a pen. There's no pen if it's 0. So we know that if x is going to be our length, of our pen, and y is going to be our area, if it's this way, we can't have x equaling 0. So we're going to have no 0. So which means the smallest one we can have is if this is 1. And if this is going to be 1, this is not going to be 29, because you have 1 here and then you also have 1 over here to make a rectangle. So what we end up with, if it's 1, our length is going to end up being here. So if that's 1, on the other side there also has to be a 1 to keep a rectangle. So that's the big thing you got to remember. We have to have a rectangle. So it's a rectangular pen, which means it has to look like this. Or as we got in our original picture, it must be this sort of shape. That's horrible. It has to be something like this. So that's our pen. So if we have a 1 over here, we've also got a 1 over here. Well, that actually means that that's going to end up being a 2. So anyway, if this is a 1, and we've also got a 1 over here, which means that's a 1 plus 1 plus whatever else is left. So that means this can only be 28 long. So if our first x is going to be 1, because if we have 1 and 1 for our sides, that makes 2, and 2 from 30 would be 28. So our y value is then 28. Because 1 plus 1 plus 28 is 30. So we got 3 sides to our fence. We got our x here. We have our width here. And then we have to have the same x over here to make our actual pen. And this is the barn. and then the area is in here. And that's what we got to have. So that's why it's 1 and 28. Because if this is 1, this has to be 1, and that's 2. And 2 plus 28 makes 30, which is all the fencing we have. We have 30 feet of fencing. So, as we continue on and keep making our table, we're going to figure out and hopefully see some kind of pattern for this. We may need more, we may not sure. So if the next one we can have is, so this is the shape of our pen here. This is our first pen, go to 28 and down. So that's our first pen. So if it ends up, if we have a X that's 2, the pen's going to look like this. So we have to have 2 here. So if this is 2, 2 plus 2 is 4. So that means we got to have 30. So that means our width is going to be 26. So apparently we have a little bit of a pattern. This goes down by 2 each time. This is going up by 1 each time. So this is now 26 for our width. So that's 30, 29, this is 28, 27, 26. And that's our next pen. Is that shape, and the area is whatever is inside. And we can figure out the areas in a second. So the next one would be, the length is 3, and then we'll go 4, 5, 6, 7, 8, 9, 10, 11, 12, 9, 10, 11. Apparently we need more. So we'll just take this out and see how far we got to go with it. So we'll take it out that far, just for fun. So if we know something, we know that if it's 3, this is going down by 2 each time. Let's just double check that. So we have 2 3s, which is 6. So that would be plus 24, which would give us 30. So now we've got 24. So if it's 4, this would have to be, that's 8, which would be 22. So that equals 30. So apparently this is just going down 22, 20, 18, 16, 14, 13, not 13, 14, 12, 10, 8, 6, 4, 2, and at 15, 0, because 2 15s, that's why. So if we look at this, 15 plus 15 plus 0 equals 30, because we have to have 2 of these. So what we're ending up with is this. We have x plus x plus our width. And that has to equal our 30 feet of fencing. So there's our pattern. So now we've got the shape of the pens. Now all we got to do is kind of draw them. So if you think of this like a string, if this is still confusing you, if this goes up 2, this other side has to go up the same amount. So this is what the shape of the pens end up looking like. So now we can kind of see our pattern. 4, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That should be 18. This went down by 3 instead of by 2. There's our mistake. So it's always good to double check your work. Let's see. If it's 1, we got 1, 2, 1, 2, 3, 4. Well, it should be 28. 1 is 28, and that's here 30. Let's make sure we got all these along here. Let's just give this a shot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Now, what's going to get tricky with this is actually going to end up being here. So let's make some sense about this. I'm going to assert that this is actually going to be like this. Just for a drawing. So to establish the pattern, this will actually end up looking this way. And here's the reason why. Because this is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Because as we move this side in, it's not actually going to the 26 mark. It's just simply, this is our x value, which is an x is the length of the first side here. So that's our x. So we just got to make sure that we count this off. But we've established a pattern. That this one here, for 1, if this is 1, and then this here is at 2, this is at 3, this is at 4, this length here, the width, has to be 22. And it is. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, even though it goes out here to where x is 26 because it's shifted over. So be careful and count that. So let's just double check so that we know that that's 22. This one here has an extra 1 and an extra 1. So we're taking 1 off of each of these and moving it in, and that's what makes the pens. So we're talking, be careful about counting length. So next one, if our pattern holds, is at 5. So if that's going to be 5, and this length here, this is 5, and so then this length here would have to be 20, which is going to go to here for a shape of this. So we got our, we're just kind of marking these things off. So this is just where the barn is. We really don't need these anymore. So this length here, this is our x, this is 1. That's 1. This is 2. This is not an xy. This is our x value is the length of the first side, 2, and then we've got 3, 4, 5, 6, 7 on up, just like that. And then this is the width of our pen. So we've got our pattern. We know this is what we got. So let's just start building. Well, that would be 0. I would go to here, and that would do that, which we really can't do, but it looks cool. So this is all the pens that we can have. So let me just shrink this down and move this. So that's just our little evidence of proof of sides. Okay, so we got, let's just see how this matches up with what we predict is going to happen over here. So I've got 7, 8, 9, 10, 11, 12, 13, and the top one was 14, and then at 15 it goes to 0 width, which makes sense. So these are all the shapes of our pen, and these are all of our dimensions. Okay, so now we've got that part. Okay, and so now what we're going to do, now we have some coordinates that we could actually end up putting on a graph, but we're not going to put 128 on the graph. We're going to put the area on the graph. So this is actually just, this is not really the area here. This is the length of x, and then this is just our width. There we go. So let's just move this thing over here for a pattern of how to get the sides. We have our little equation here already to get the length, but we don't have it for area. Now area is going to be our y value. This is what we're going to be plotting. So what we have to do is adjust our table to include the area. And then once we have that, we'll have the points that we're able to plot. Keep in mind, I'm not asking you to do anything that I myself am not also doing. We don't need to include that one because that's 0. This has no width. Therefore, no area. Okay, so we don't have to include that. So in this one, the area here would be 0, which we're not going to include, because that would just be weird. So that's here. Area is 0, and that would not be cool. And probably if we had a 0 up here, the area would be 0. So let's just double check that. If we have 0, then the height or the width of it would be 30, but it would still give us an area of 0. And you can go ahead and do the math on that yourself, because 0 plus 0 plus 30 30 is 30. And 2 15s make 30, so same idea. All right, so here we go. So now we're just taking these and we're multiplying them together to find out which one has the maximum area. And if you were to go in and take each of these, this area is just the dots under the boxes here. The area is the space inside. So the area is going to be our x value times the width. So that's all we have to do for area, because that's just what our length and our width are. And length times width equals area. So this is just 1 times 28, which is 28. This is 2 times 26, which would be 52. And that's a big jump. And then we have 3 times 24. So that'd be 72. That's 72. And then we got 4 times 22, length times width, 88. 5 times 20 is 100. 6 times 18 is 108. 7 times 16 is 112. 8 times 14 is also 112. 9 times 12, well, that's 108. And then this is 100 because it's 10 times 10. Then we got 11 times 8, which is 88. And we're seeming to see a pattern here. It goes up, hits 112, then goes back down. So somewhere in here between 7 and anyway, you'll figure that out. Then we go 72, 52, 28. Fourteen times 2 is 28. 13 times 4 is 52. 12 times 6 is 72. So yeah, that's what we got. And then we would have this 0 would be on the other end, if we were to put the 0 up here, but we didn't, because you can't have a width of 0. But I suppose we could have something in between it. So we now have our x's and our y's. Our length is area, or our length is x, and the area is y. And that takes us here over to our graph. And we have a lot of points on that graph. Holy smokes. But anyway, I'm going to take and transfer and use this information with our x's and y's and put it over here, and then we're going to plot our graph. Okay, so here I've taken our table and I've put it in with the graph that we're going to use. It's wide, it's tall, it's huge, it's small, all these sort of things to make it fit on one screen page so you can see it. But we don't need the width for graphing, we just have the length and the area. And we're going to plot these points and see what we end up with and get. And it doesn't have to be quite perfect. It just needs to be good enough to show an idea, because in the end of this, we are going to prove algebraically that what we have is a maximum area. So first off, what we got is, let's just see here. Our area, our x is 1. We have an area of 28, so we got to find 28. Now each of these lines here is going up by 5, so it's 5. So what we got here is we've got, let's see, we got 5, 10, 15, 20, 25, 30. So we're going to have to approximate some things, but we'll get the general idea of what this graph looks like. And then when we're done, we'll shove it into Desmos, and you'll see that what we got is actually what we have. So let's just work on this right here. So I'm going to put, I'm going to use, if one, this is our x-axis, is the length of our that touches the wall. So the length of the side that's touching the wall. So it's the side length that touches the wall. Side length on the wall. And our y values, of course, that's our area. So this right here is going to be our area. So that's our y value is our area, which is green. And so I'm going to be plotting, I'll go to the x, but I'm going to use green dots to show where the area is. And so that's pretty much I guess, the most important thing. So here we go. So let me just grab my dots here. See if that's big enough to do. Yeah, that's perfect. Okay, so when it's 1, we got 28. So we got somewhere around here. When it's 1, it's 28. Now, then when it's 2, we got 52. 2, it's 52, which is pretty much right here on the 50. Put a dot there. When it is 3, it's 72. So we go 3, 65, 72, which is pretty much close between that and 75. So it's actually right here. I'm going to go back down and move this up to 52. Pretty close there in between 50 and 55. And it seems to be that we've got a curve, and that kind of matches our data. Okay, then we got, then we've got 3 and 72, 4 and 88, 60, let's see, that's 80, 85, 90, 88 is between 85 and 90, so right there. Okay, and then we've got 5, 100, that's nice. And then what we have is 6, 108. And then we've got 7, 112. And then we also had 8, 112. And that should look pretty familiar to you. And then we got, because it's starting to go up, and then it's probably going to come down, which it does because we know this. 9, 108. 10, 100. And then we have 11, 88. And then we have 12, 72. Yep, pretty good. And then, because on one side of the axis of symmetry needs to match the other side of the axis of symmetry, 1272, 1352, 1428, and of course when we had 0 and 15 it was 0, but we couldn't include it, so we're going to lose an open circle here because we cannot include that because we've already determined that that is a area of 0. So this is a graph of our areas. And it appears to be there's probably somewhere up in here a maximum because that's the highest it goes, somewhere up in here. So we know that somewhere up here in between 7 and 8, like 7.5, is probably going to be the peak, which is probably something like, I don't know, we don't quite know what that is, but I'll mark it in, I was going to mark it in red, I'm still going to mark it in red. Actually, I'll use purple for that. Use this funky purple. Okay, so purple, we're going to have somewhere up here, we're going to end up with a maximum. So this is where our maximum would be. So our maximum is somewhere up here, between 7 and 8. Between 7 and 8. So that's our maximum between 7 and 8. And down here, we do not include this because we can't have a length of an area of 0. So that's why we don't include these. But the shape in general appears to be an upside down parabola. Otherwise known as negative parabola. So we have an upside down negative parabola with a maximum between 7 and 8. So if we make, so basically that's the side length, maximum between 7 and 8 feet, 7 feet and 8 feet for the side touching the fence. And that is what it shows graphically. So the point on the graph representing the pen with the greatest area. What are the dimensions of this pen? We're going to have to figure that out. But apparently, it's somewhere between 7 and 8. So we could say 7.5. Let's just go with that. So if we go with the 7.5 dimensions of the pen, if we were to take 7.5 plus 7.5, that is equal to 15. And if you look on here, and what is, so that's 7.5 here. 7.7.5 is 15. So we know then that we have to add 7.5 plus 7.5 plus 15 is going to equal 30. So that's all of our fencing. So what we have is a pen that looks like this, approximately. So if this is our barn wall, And our x height touching the fence would be something like this. Our width is then going to go over this way. Oops. Our width then goes this way. And then, of course, we have the same length on the other side, right here. So this, we could say, we're going to hypothesize, it's like 7.5, between 7 and 8, and then this is going to have to be 15. And what's the area? Well, the area is, and then we have the area in here, and the area is just simply, so our area, in this case, is length times width, which would be 7.5 between 7 and 8. So we got 7.5, which is our length. And then we've got our width, which is what's left over to make the 30 feet of fencing, because perimeter has to be 30. 7.5 and 7.5 is 15 and 15 is 15. So it's looking like the max area, according to what we have so far, our area max could end up being 7.5 times 15, which is 112.5 roughly. And so this is 112.5. We're going to hypothesize. We don't know for sure at this point. So it's 112.5 feet, but it's square feet because it's area. So that's just based upon what we would know, and we would want to include that in our poster from this. And if we look at that, that's 112.5 between, and when it's 7.5. And so doing this, we just verified with our graph. So we have a max between 7 and 8, which is roughly, this is approximately, or we'll say this is 112.5. Do that a better way. For our max, which would be the top. $112.5. There we go. So now we have it on a graph. In our table, it's somewhere in between 7 and 8. So this is where a max would be. Max in between. Right here. So our maximum would be somewhere in between these because it goes up and comes down. And it's not, so it's roughly that. And we got that according to here, another representation using a table. And we've kind of analyzed it. What general shape do we have? Well, we have an upside down parabola. Upside down parabola curve. We have that. It's at 7.5, 112.5 is our coordinates for that. And so now we're here. So we've kind of got a picture of what the max area could be, proven by a table that's in between here, which is this 112.5. And we wouldn't include the zeros because then we would have no pen. So we don't include these because there's no pen. That's why they're open circles. Okay, so now an equation. So these are some tips that you can look at and check it. If the length of the sides were attached to the barn are X meters long, and if she has only 30 meters of barbed wire, what's an expression for the width of the pen in terms of X? We're going to build this. So now we're going to write an equation, and what kind of graph should this equation have? Well, we know it should have an upside down parabola. And in our equation, we're going to have y equals 0. What are the roots? But we know that we can't have an area of 0, but we're going to find it anyway. We're going to use the equation to find the vertex. So we're going to use the vertex form, which is when y is equal to x minus h squared plus k, and the vertex is at h and k. And that will actually give us our maximum, or it also gives us our minimum. That's the point in the at the highest or lowest of the curve. So that's our vertex form. So our vertex is going to be at the point h, comma, k. And so we might have to do completing the square with that. We're going to use the results to find the largest possible, and then figure out what the dimensions are of the pen, provided it has to be a rectangle. Personally, I do an arch, or something close to a circle, but we're limited to a rectangular pen from our problem. So let's put this all together here. So we know that if we look at our pen again, or get a picture of our pen, it has to look like this. So this is what we're working with. So we take that picture and we can put it here, and we can start working things out based upon our picture. So it's always good to have a picture. Okay, so I'm going to redo that here real quick. So what we've got is we've got our barn. So this is our barn. And then we've got our X value for the sides. So whatever this is what it is. And that's our X. And then we have our width. And then we have another one of these. So I'm going to clone that. And that goes here. So this is a basic representation of what we have. And this was X. So this is also X. And then to get this, you take X and X, which is 2 X's, and we subtracted them from 30. So we know that X plus whatever our length is, actually this is our length, plus our width, that has to equal 30. So we have 2 X's plus the width. And that has to equal our 30 feet of fencing, because that is the perimeter that we can build, because we don't have to build the barn because the barn is already there. So this is our basic starting point for what we know. And then inside here, this is where our area is. This is the area, which is length, which is our x times our width. So what does all this mean for us? Well, basically, the width is simply going to be 30 minus 2x. If we look at this, so the width is equal to 30, and we take away our 2x's by subtracting this out of this side. Subtracting on this side is just 30 minus 2x. So that's what our width is. So that's our width. So if we're going to look at what does that mean for our area, well, since area is equal to length times width, all we need to do is take, since this x is our length, and our length is just x here, so we have length and width. I'll put length there, so x is our length. We simply have x times 30 minus 2x. And that's what our width is. So if we do some multiplication, we can then see that our area is equal to then 30x, 30 times x minus 2x squared, which can be rewritten into a little nicer form, and I'll put it up here, of negative 2x. Negative 2x. So once again, that's negative 2x squared plus 30x is equal to the area. So now that we have this for our area, I'm going to do something beyond the book right now, which is I'm going to actually do completing the square with this. And the way that you do that is you can factor out this negative 2. We're not going to divide by it. We're going to say that that's negative 2. We're going to pull it out and unfactor it. So that's negative 2 times x squared gets negative 2x squared. This, since we're pulling out a negative 2 from everything, we now end up with, this is going to be negative 30x. And I'm just going to put a plus 0 here to hold space, and that's going to equal 0. So we're now I'm going to factor this and show how to complete the square with this. And since, well, it's actually not 30x, that's going to be 15, because we pulled out the 2. 2 times 15 is 30, so that's negative 15x. Because if we distribute this, we get this equation. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 15 is positive 30. So I have unfactored, or undistributed rather, otherwise known as factoring. I undistributed this negative 2 from all of this, and this is what I got. So this is what we now have, and I'm going to do this and leave a little bit of space here. So this is now what we have, and that equals 0. And we got to come up with something to complete the square here. So we're going to add in here something that's going to end up completing this square. I'm going to leave this as a square here. And so leave it as a square here, and then we have to add that to this side at the end. But remember, it's also multiplied times this negative 2, because this is all negative 2 times everything in here. Well, we know that if if this is going to be 15, it's going to have to be 15 over 2 because it's always half of that. So what we end up with is negative 2 times x squared minus 15x, and we're going to add to that 15 over 2, that's squared. So we now have our equation. This now becomes 0, and since we added to one side, we added 15 over 2 that's being squared, but it's also multiplied times a negative 2. So that's the whole thing that we've just added to both sides. So this piece right here, this is our square that we have added. So here's our square that we've added, but it's also multiplied times a negative 2. And of course, we all know that this 0 really doesn't matter anymore. So this is what we added to the left side, so we also have to add it to the right. And we know that 15 over 2 is 7.5. So this is going to equal x plus 15 over 2, and that is now a perfect square, but it's also multiplied by negative 2, and that's going to equal negative 2 times 15 over 2 squared, which is 225 over 4, otherwise known as now 15 over 2 is just 7.5. So if you like using decimals and squaring, that's fine. But this is just going to equal that 2 and this 4 are going to cancel. So we have a negative 225 over 2. Here we have negative 2 times x plus 15 over 2 squared. And that's what's equal to that. And to put it in the HK, we just go negative 2 times x plus 15 over 2 squared, since we're going to move this over, plus 225 over 2, and that equals 0. And now we have it in the y equals x minus h squared plus k form. Now, if we take this to make this match up, 15 over 2 is just 7.5. 225 divided by 2. Interesting. 225 divided by 2 is 112.5. And 15 over 2 is just 7.5. Sorry, I seem to have made a sign error. This is a minus, because that's a minus. And this should also be a minus, but it's not going to matter. So it's minus, minus, minus. That's a minus. It doesn't matter because we square it. And so this is what we have. Negative 2 times x minus 7.5 squared plus 112.5. Well, this is h, this is k. So our vertex is at 7.5, 112.5. And that is exactly what we got before. So these are all the things that we have to include in it, and we have all the data here. Now what we can do is take this equation and put it into Desmos, and you'll actually see the graph and everything that matches up with it. So that's what we're going to do right now. So just for a recap, we have our equation of negative 2x squared plus 30x. That's equal to our area, which is our function. So we could write f of x is equal to a negative 2x squared plus 30. So there's our equation, and this is just y is equal to negative 2x squared plus 30. Sorry, I keep forgetting that x, plus x. So this is our equation, and that's what you put in the Desmos. So right now I'm at Desmos, And oops, if we put in here y equals negative 2 x squared, negative 2x squared plus, and you see we got an upside down parabola there, plus 30x. We then have to zoom out a little bit. And so this is what our shape is, and I'm going to adjust the settings on here to make this go from exactly what we had, which was on our x-axis we went from 0 to 120 before, and then this is actually that went from 0 to 15, and then this is going from 0 to 120, and we're going to do it by ones and see how that ends up looking. So that ends up looking like this. So if we pull back from that, and here I'm going to put a constraint on x. Let me see if I can do that now. If I highlight the x. So this is our parabola here, and then I'm going to put a limit on it, or a constraint, that x has to be greater than, actually y, I'll just put y, the area has to be greater than 0. See if that works. There we go. So that's it. And that, my friends, is our graph. And if we can get a little closer to it, so this is what we have for our graph. Right here. And we said it had to be greater than 0, so that's 0, 0, so that doesn't work. If we go up here, we get 7.5 and 112.5. And here we have 15 and 0. So that's what we end up with when we do the graph of that. So what you would do then is you take that. So this is everything that we've been talking about, and we just proved it algebraically. So once again, we have our maximum here. Remember, this is our area. And this was the side that touches the fence. The side length as it touches the fence, or touching the barn rather. Side length touching the barn. This right here, this is our maximum area. And it's a maximum because we have an upside down parabola. Or a negative parabola. We'll call it a negative parabola. And if this is the maximum, and since that's the maximum area, we also proved this algebraically by completing the square, and we ended up with negative 2 times x minus 7.5, and that was squared, plus 112.5, and that equaled 0, and that gave us our vertex at 7.5, comma 112.5, and that was our maximum because this parabola is facing down. So this is our maximum. So this is the maximum x, this is our x value, and then this value being y, that's our area. And so that's how we can prove, not just algebraically, but graphically, that this is the largest area. So once again, for a poster, I would definitely have our equation and then show completing the square, show work to find the vertex, which is at HK. I would also include somewhere on here, put your table, and show where the max is. Show the maximum area using the table, just like we did. Then you'd also want to have your graph of the parabola that we did, and showing the maximum. Also include the fence or the pen diagram. And then finally, I would definitely want to include, possibly somewhere on there, the Desmos graph. So what I'm basically asking you to do is go through this work and then create that poster, showing everything that we did here. So once again, you want to have your graph, and we built one, and also have the graph from Desmos. You'd also want to have the pen diagram where we built the pens. You put the pens in there. Then you also want to have your table. And then you also want to have, with all of this, the equation work and vertex form, that vertex form of the equation, which I'll call the vertex work. And so that's pretty much what should be on your poster. And then kind of draw and show and label. Draw, show, label, and also link everything. So make sure of that. And basically we've proven that the largest pen is what it is. It has the X value of the side touching the barn of 7.5. And the long side, or the width, is 15. So the dimensions, I don't know if I put this in here, but we proved that the dimensions are going to be 7.5 by 15. 7.5 by 15 are the max dimensions. Will give us the maximum. Equals, that's actually what gives us our max area. So, don't forget the review preview. Good luck. This is the only one for this week, so do well, take your time, and I'll look forward to seeing your posters. You don't need to submit, well, you could, I will need to see the notes, but I'll also need to see your poster. So for this week, there's notes and poster. And you can do that with Google Docs or HandDraw, whatever you want. Take care, bye.